tested about it before. So here, yes. So if you have gone through the last class, you have seen that over there we were talking about the different types of confirmation analysis, right? And the confirmation analysis, what we have done is, I'll share my screen with you. In the confirmation analysis that you can see over here, what we have done is we have talked about different confirmers and how they can be stable in there. And over there was one more topic that we have talked about is for cyclohexane systems. What all different confirmers are there, and what are their different types of stability or in there as well. These are the basic things that we have discussed about in the last session. All right, just 1 second. Just give me 1 second, guys. Yeah. Yes. So over here, as I was saying, in the last class, we have talked about all those confirmation analysis and stuff. Now, today we'll be talking about the different types of name reactions. Now, before I start the name reactions, this is something that we have to talk about first. Yeah, the SNI mechanisms. So this is what we are going to talk about first. Okay, but if you have watched the last video over there, we have definitely talked about the different conformers of cyclohexanes, right? So on the basis of that, we'll try to solve one question right here, which is this is a PYQ, previous year question, which is this one. So in the last class, I taught you that the cyclohexane, they can be there in the boat and the chair, the half chair and the twist board. These are the basic conformers that we can get the cyclohexanes in. Now, as you can see over here, I am drawing the boat conformer as it is the most stable conformer out there. Now, there is a molecule that I have drawn over here. It's a cyclohexane, and on the top you have a tertiary butyl group, and the bottom you have only a methyl group in here. So, what do you think, guys? Out of this A, B, C, D, which option is correct? Which was the most stable conformer of cyclohexane from the last class's discussion? What do you think? So, Laksha, Kokul. With respect to the 4 conformers that you see, which conformer is the most stable for cyclohexanes? These are all actually, the buffer kind of things. Like it is there, like the cyclohexane is there in your syllabus, but all these conformers and all those things, they are not really mentioned in there. That doesn't make it excluded from your syllabus. Actually, they don't ask you this question so far, but if they do, you can't really ask any questions to that thing. Okay, so no, that is not correct. So try again, Gokul. Okay, see, now in the cyclohexane conformers, always remember this is the bulky group, right? Whenever you have a bulky groups like tertiary butyl or something like that, what you have to remember is you can never keep the bulky group in their axial positions. So bulky groups are always kept in the equatorial positions. Now, what do I mean by axial and equatorial? When the bonds are like this, that is called axial bonds. When the bonds are like this, that is called equatorial bonds. So if we talk about a cyclohexane molecule, I've talked about the chair conformer in the last session, but not really discussed about it that detail in that detailed manner, right? So you just need to know only these things that I'm saying right now, that there are two hydrogens connected to every particular carbon. So they are like this way. Don't really have to know what anything extra other than this, what I'm trying to say here. So this is the two molecules. So every carbon has an axial bond and an equatorial bond, every single of them. So the straight bonds like this one, these are the axial bonds, and the tilted one, the slanted ones, they are the equatorial bonds. So this is axial, this is equatorial. This one is axial here, the lower one, this one is equatorial. Here the upper one is, above one is axial, and the below one is equatorial. Here also the above one is axial, the below one is equatorial. Here also this is axial, this is equatorial. What did I tell you right now? We would never keep the bulky molecules, bulky elements in the bulky groups in the axial positions. Okay, we'd always have to keep it in the equatorial position. The reason is something that would take a lot of time to discuss about it. Only if you want to know about it. This is known as 1,3 diaxial interaction. There is something called 1,3 diaxial interaction. Because of that, we cannot keep it. But guys, I would suggest you not to go into that details right now. Just keep it like we just cannot keep it for the time. They won't ask you questions from this much of details. But the reason is you just avoid the groups to keep it in the axial position. So why would you keep it then in the equatorial position? So option C is not the right answer because it is there in the axial position. That is not the right answer. And option D is also not the correct answer. It is either of option A or B because in both the cases the bulkier groups are on the equatorial position. All right. So whenever there is any group, actually try to avoid it to keep it in the axial position, because whenever you keep it in the axial position, it is not really safe. Okay, none of the groups. Okay, now considering the statement I have just given you, what do you think? Is it option A or is it option B? Which one is most stable conformer? Try to do this now. Option A or option B? Which one is comparatively more stable in here? No, Raksha. See, like I said, in option B again, you are keeping the methyl group in the axial position, right? Axial means whenever the bond is like a straight line. Whenever the bond is slanted, that means that's an equatorial bond. All right. So this is also an axial bond. And I just told you guys, try to avoid keeping groups on the axial position as much as you can. As you can see in here, both the groups are on the equatorial position. Who is axial position then? Who is holding the axial positions? The smallest elements, which is hydrogens. So keeping hydrogens on the axial position is fine, but not the groups. If you have a chance, if you have an option, try to keep them in the equatorial position. So as here, both the groups are on the equatorial position. Option A is the correct answer here. So this was completely based on the last discussion that we had in the last class. Okay. So right now, in the next few classes, starting from today, we'll be looking into all the reactions those are there in class 12 and class 11 combining together. So all the special reactions those are there, all the name reactions those are there, and some of the extra reactions as well, just like Borodin-Hunt-Dicker, Perkin reactions, Claisen rearrangement, Claisen condensation. These are different things. We'll be talking about these kind of reactions as well, name reactions as well, which are not really there in the book. So they don't really ask you any questions from the book, but what they do is they give you a reaction and they go like, which one of the following is the correct answer? So they just go like A, B, C, D. In those options, they can keep this reaction like Perkins reaction, or they can keep like Hunt-Dicker reaction. Okay, so they would keep it like that. We all know that option is not going to be the right answer, But still, when you'd be solving these questions, what happens is sometimes you feel like not that confident, right? When you know the reactions, what is going to happen in those reactions, you'll be much more confident to solve those kind of a question. Any which ways, like if you see those kind of a questions in NEET, what would happen is, as you can see, the two options you have no idea about, you have never heard those reactions, you just skip the questions right away, right? So that to avoid these kind of things, we would be going through those specific name reactions in the further classes as well. Now, as you can see over here, guys, that the reaction mechanism that we are going to talk about is called SNI reaction. So have you ever heard about this, both of you? Have you ever heard about this reaction? No? Okay, we haven't. So we have heard about SN1 and SN2 before, right? And we have done this reaction already. We just do not know about this reaction so far. So we have talked about SN1 reaction. We learned about SN2 reaction, right? These are the two substitution reactions. If I have to give an example of SN2 reaction, see, most of the reactions that we have seen in organic chemistry, most of them are SN2 reactions. Okay. And SN1 reaction, I'm going to talk about, like, I'm in the next further classes, we are going to go through all the name reactions. There I'll be specifically mentioning which one is SN1 and which one is SN2. And I have to tell you, in some of the reactions, you won't even recognize it, the type of the reaction which was happening. So I'll be talking about that as well. So now, SN1 is substitution nucleophilic unimolecular. And SN2, if I talk about that, it's bimolecular, right? So I'll just ask you a simple question right now. Okay. Let's say I have a molecule which looks like this. If I ask you now, what kind of mechanism is it going to undergo? As you can clearly see, it is a 3 degree. It's going to be 3 degree systems are always going to undergo SN1. We know this. SN2, 1 degree systems. If I have to make it undergo substitution, if I give any nucleophile here, then what would happen? The first one would undergo SN1 and the second one would undergo SN2. We know this. Now, if I give you this molecule, let's see how good do you know about the SN1 and SN2s right now. If I give you this molecule, try to solve this. If I give you this molecule, and if I add HBr on it, which mechanism would it undergo? Which mechanism would it undergo? Guys, this is just an addition of HBr here. In one carbon, you'd be getting hydrogen, in one carbon, you'd be getting bromine. But which mechanism is it going to undergo? SN1 or SN2? That's the question. Try to solve this now. Anything so far? That's correct. Very good. It is going to undergo SN1 mechanism. See, it was a difficult question because we never knew whether it's going to undergo SN1 or SN2 because, see, first of all, what happens is whenever we try to add a particular element, particular molecule in a double bonded system, what is the mechanism that we follow? What's the name of that name reaction? It's not a name reaction, it's a rule kind of a thing. So addition on an unsaturated double bond follows Markovnikov's rule, right? Now, what is Markovnikov's rules? According to the Markovnikov rule, the carbon having lesser number of hydrogen would get the bromine, right? So according to the Markovnikov rule, you are supposed to get this as a product, isn't it? We're supposed to get this as a product. Now, according to which rule, guys? According to Markovnikov, we get this. Now, do we know which pathway Markovnikov rule follows? Is it SN1 pathway or is it SN2 pathway? Come on, guys, think about it and tell me. Markovnikov rule, which pathway does it follow? Is it SN1 pathway or is it SN2 pathway? See, like I said, we have learned a lot of reactions out there before, but we never really paid attention. Just a second, guys. There is a problem in my mic right now. All right, like I was saying now. So here what happens, it undergoes SN1 mechanism. Now, how do you know this? This is actually the Markovnikov rule was actually the outcome of SN1 mechanism, right? Because see, if there are two carbons sharing the double bond, okay? Now, HBr breaks as H plus and Br minus. Okay, listen to this carefully, very much. Now, the double bond goes and takes the hydrogen as a nucleophilic cation. So what do we get over here then? CH3, C, CH3, CH3, CH plus single bond, CH2 as the double bond has taken hydrogen, so we get this molecule. We get a positive charge on the middle carbon. Now, as we get positive charge on the, and by the way, why do we get this? Because it's a 2-degree carbocation, right? 2-degree carbocations are stable. That's why we get the positive charge on 2-degree carbocation. So because of that, what happens is it is comparatively more stable system, right? Now, as it is comparatively more stable, what would happen is now the bromine Br minus would come and gets added up here. That's how we end up with the Markovnikov rule. All right. But actually what happens over here is, as it's undergoing SN1, that is something proven. Now, in this particular molecule, this is not the exact product that we get. Do we know what's going to happen now next in this molecule? It is going to undergo methyl shift. All right. Like I said, guys, this is all special reactions we are discussing about. So it's going to undergo methyl shift, CH3 shift. Have you practiced this question before? It was there, right? In NCERT as well, this topic was there. Okay. And the plus charge would come over here because the methyl group has shifted. So as a result, the plus charge is now here. It is now a 3-degree carbocation. So it is even more stable than the previous situation. That's why, guys, the methyl shift happens. And because of the methyl shift, what would happen is now the bromine would come and connect over here. So what would you get? CH3, C, CH3, Br, CH, CH3. This is the final product because the methyl shift. All right. Are we clear? Write it down now. Good. So let's practice one question then of the methyl shift or something else as well. So if you have gone through the JEE papers of this year, you'll be seeing these kind of questions are being asked a lot of times. Considering that we are expecting, like as I have told you before, that you can expect by looking at the JEE papers, you can expect you can get an idea about the NEET papers as well, which is going to come this year. So I'm expecting that the methyl shift or these kind of bond shift kind of questions are going to come. So let's say we have this molecule this time, and I'm adding HBr on it. So what would happen in here? What is the final product of this molecule? Try it down now. Follow the mechanism. Okay. If you just try to remember the Markovnikov rule and all, it's not going to help you. Follow the mechanism always. That is always going to help you. Done. First, definitely you are breaking HBr into H plus and Br minus, right? Then you are asking the double bond to grab the hydrogen as before. So what would I get from here? So I'd get CH3, C, H, CH3, single bond, C, H, single bond, CH2, and H. I'm asking the hydrogen to connect with this carbon again because of it's a 2-degree carbocation, which is going to get generated at first. Okay. If the carbocation gets generated in this carbon, it would be 1-degree carbocation. So I'm asking it to I'm just writing this one because this is the major carbocation because it's a 2-degree one. So this is going to get formed here. Now what would happen? What do you think? It's a 2-degree. Is there any way that you can make it 3-degree again, or any better stabilities that you can form? That's correct, Laksha. There's going to be hydride shift. So by shifting the hydrogen this time, you'd be getting, these are called rearrangement chemistries. You know, this, the hydrogen is coming there. Now the bromine would come and join in here. So you're going to get the product, which is called CH3, C, CH3, CH2, CH3. That's how we do this. Okay. So these are the things. Now let's try another similar kind of question. Okay. So let's say I have okay. Now here, if I add HCl or HBr, what would be my final product? What you have to do is you have to write the name of the shift, if there is any, Otherwise, you just have to write like just write like, let's go like this. There's carbon number 1, there's carbon number 2, there's carbon number 3. In which carbon the chlorine would sit? What do you think? Try to solve this now. In which of the carbon number 1, 2, or 3 would the chlorine sit? Anything? Okay, let's see whether it's the carbon number 3 or not. See. So first what we do is always see, whenever you would be doing the organic chemistry now, always draw all the possible products that you can have from there. And then you compare the stability for them. All right. So what are the possible products for this? So first, this would break into H plus and Cl minus. And the double bond would go and grab the hydrogen. Now, where is the hydrogen going to come? So as I said, it's going to come to the carbon where you have like it would try to make a carbocation which is comparatively more stable. All right. So see, the first situation that you can make is you can let the hydrogen join through the carbon number 2. So if let's try it in this way. So hydrogen goes to carbon number 2. In that situation, what would happen? pH, pH, pH. Then we have hydrogen is coming to carbon number 2, so there is hydrogen in there, and the carbocation would form in the carbon number 3. This is what we have. And if the hydrogen comes to carbon number 3, these are the only two possibilities, right? Either the hydrogen can come to the carbon number 2 or carbon number 3. If it goes to carbon number 3, then what is the structure that we can have? The hydrogen is here. Now tell me which one is more stable? Molecule X or molecule Y? Be quick. Which one is more stable, molecule X or molecule Y? You can clearly see that the molecule X over here, it's a 3-degree carbocation, isn't it? And you can clearly see molecule Y over here, it's a 2-degree carbocation. So which one is more stable? With respect to carbocation, molecule X is more stable, right? That is what you were thinking so far. And that's why you said that the PR is going to come to carbon number, like this carbon number 3, right? So the product you were expecting, Laksha, is this one. Oh, this one. But instead, this is going to be the carbocation which is going to form. This is not the major product. This is going to get formed, but not the major product. Why? Because now there can be a hydride shift. And if the hydride shift happens, so far it's not stable. But right after the hydride shift, do you understand what's going to happen next in the hydride shift? You can clearly see that this is also a 3-degree carbocation. This is also 3-degree carbocation. This is also 3-degree carbocation. But this 3-degree carbocation is more stable than this 3-degree carbocation. This one is more stable. Why is that? What is the possible reason behind it? This 3-degree carbocation is stable because of 3 plus I effect showing group, isn't it? Or you can say hyperconjugation, whatever you like to say. 3 plus I effect showing group. But here we have 3-degree carbocation where I have 1 plus I effect and 2 plus R effect. Phenyl ring shows plus R effect. It shows resonance. So that's why, guys, this carbocation is more stable. So that is why it would come through this pathway. So this was a tricky question, as on the very first place, when you draw them, you won't be able to see the trick in there. You'll clearly go like for this one. But then again, after this hydride shift, this molecule is even more stable. So guys, the bromine is going to come and join in this position. That's going to be the product. Was that understandable? Was that clear? This is the kind of a questions. This is just the beginning. This is the type of a question that they are asking in JEE this year. You can open up any particular shift, you would be able to see the hydride shift, the methyl shift, the bond shift. I'm yet to teach you about that. The bond shift is also coming into the topics. Are we clear? Can I move on? Yeah, then? Okay. So now let's solve a question which is something which is out there in JEE, which came in JEE according to the memory-based papers. Okay. Now see what they're asking is, they're given this molecule. And they're saying what would happen if I give H plus in this molecule. If I give H plus, then what would happen, possibly happen? This question was there in yesterday's paper, like in 29th January's paper. In there, they have asked this question. In 24th January's paper as well, they have asked this type of a question, similar kind of a question as well. In 25th also, they have asked a similar kind of question. So what is really going to happen here? First, I would like to know from you, what would happen over here? Like, first of all, definitely, let's say I'm giving H plus. Let's say I'm giving HCl. Let's not give H plus. In the JEE paper, it was given as H plus. But here, as we are just beginning to learn all these things, so I'm giving you HCl. All right. So what do you really feel going to happen right now? It is definitely going to be a substitution or elimination kind of a reaction. Substitution only. It's going to be a substitution reaction. What kind of substitution? SN1 or SN2? What do you think? It's a 2-degree system, so it's not really very simple to say. 1 degree SN1, 2 degree, 1 degree SN2, 2 degree SN1. I mean 3 degree SN1. What is 2 degree? Is it going to undergo SN1 or SN2? When do we really understand that it would be SN1 or SN2? SN2 always. SN1 only when the carbocation or whatever is getting generated is same. So by somehow, if you just try to do it in this way, try to make it undergo SN1 once. See whether there is a stable carbocation that you get or not. If you get a stable carbocation, then it is an SN1. If you don't get a stable carbocation, then it's SN2. Considering that, what will be our answer? And that's correct. So it is SN1. Now, why is that? Because first, what would it do, guys? H plus Cl minus. That is how it's going to break, right? Then the lone pair is going to go and grab the hydrogen. It's going to become this. Then this system is going to leave. As I said, it's going to undergo SN1 reactions. What is the reason behind this? That is what we are going to see now. Now, see, this is a very tricky question. Now, what do you think? What would happen? What do you think? What would happen next? After this, what would happen next? It's a 2-degree carbocation. Can I make it more stable than this? Can we make it more stable than this? Anyhow. See, if this hydrogen shifts, Then what would happen? If the hydrogen shifts, then from wherever the hydrogen has shifted, that position would be positive in charge. Then it would become a 3 degree carbocation in this situation. Is that clear? So if I make a hydride shift, first write it down. Is that clear? It will make a 3 degree carbocation, which is supposed to be more stable, isn't it? Exactly. So it's supposed to be more stable. It's a 3 degree carbocation, but it's not stable. It's not more stable, although it's a 3 degree carbocation. Anyone? What's the reason behind this? See, we just call them exceptions when we see these kind of questions. But try to understand the reason behind. There is a valid logic behind this. If you understand the logics behind this, things would be very, very simple for you. So what do you think? What is the valid logic behind this? Not making this transfer. See, what is the bond angle of a 5-member ring? It is close to, we know that it is close to 105 degree or 109 degree, something like that, right? The moment you make it sp2, right now it would be sp2, right? After this shift, I do understand this 3 degree, but it is sp2 as well. Now for sp2, the bond angle is supposed to be 120 degree, right? But the bond angle, it's a cyclic system, it's a constrained environment. It's not like it can just release itself. It cannot do that. It's a constrained environment it is under. So considering that, the situation it is under, if I give a positive charge, we are not stabilizing it, we are actually destabilizing it. Because it is in a constrained environment, and I am trying to make the bond angle to 120 degree right now by making it sp2, which means I'm putting an angle strain on it. It's just like if I have a cyclic system, like let's say, if I have a bond like this, all right, this molecule is there, right? Now, if I want to convert this molecule, like you can see that it's an open system, right? It's an open system. There's no such angle in there. But let's say there is a restriction. Let's say there's a 5-member ring or a 4-member ring which is in there. That'd be an restriction in there. There's a particular bond angle in there. Now, if I want to increase the bond angle, what I'm trying to do is this is what's going to happen. You just saw that the bond just got broken out, right? So if I try to enlarge it, what would happen is the bond is never going to be stable, right? There's a particular bond angle for everything. So the 5-member ring is going to get broken down. So that's why, guys, this is actually by putting it a positive charge, we are putting it under angle strain. Is this particular concept clear? By giving it a positive charge, we are putting it under an angle strain, immense amount of angle strain, because the bond angle is 109 degrees something. Okay, whereas keeping it to 120 degree right away, it's just putting more pressure on this molecule. So this is not something that we would expect to happen. Now what's going to happen? So guys, here this question actually came in here. Here we are going to see a bond shift. An entire bond is going to shift this time. Okay, before we do that, first you just name the carbons any which ways. It's like not according to the IUPAC, any ways you want to. This way. Now what happens actually is, guys, this 5-member rings bond shifts and makes it a 6-member ring. Now see, it was constrained because of the ring, right? Now if I make a bigger ring, actually what I'm doing is I am releasing the angle strain to it. It had an angle strain because I have forcefully put it in a ring system. By making a bigger ring, what I'm trying to do is I am giving it more room. I'm increasing the angle. So guys, the bond shift is going to happen. Now this is something completely new to you, isn't it? Have you ever seen bond shift happening before? Like this? No. So as you have the bond shift, when that happens, first of all, what's going to happen? See, don't try to do it now. After from here, don't try to draw the molecule according to the way you see it. Don't do that. You'd get wrong answers in that cases. First, you tell me it was a 5-member ring so far. The moment you expand this bond and add this carbon inside a ring, like what I'm doing right now, I'm breaking the bond. Okay, breaking this bond between 4 and 3. I'm adding it with 2. and I'm adding it with 2. So it is going to be, if I do that, it's going to be a bigger bond, bigger ring, 6-member ring. From 5-member ring, it would become 6-member ring because I'm adding the carbon number 2 in there. So first, what you have to do is, first you draw a 6-member ring on your own without thinking about anything. Just draw a 6-member ring. Then which atoms are combined together? This bond is going to broken up. Carbon number 4 is going to get attached up to carbon number 2. You just give carbon number 4 and carbon number 2 to any 2 adjacent atoms. All right, 4 and 2, any 2 adjacent, and then just see who are they connected to. So 4 is connected to 5. This is going to be 5. 5 is connected to 6. This is going to be 6. 6 is connected to 7. This is going to be 7. 7 is connected to 3. This is going to be 3. Then 3 is connected to 2. As you can see, 3 is connected to 2. I've drawn that. 2 is connected to 1. So there's a middle. Tell me, is that clear? Raksha, Gokul, is that clear? Okay. Now, after doing this entire shift, now focus. What happened again? There was a bond in here. This bond got broken, right? And connected like this. So this carbon now have 1, 2, and 3. Three bonds. It had 4 bonds, right, before, when they were connected together. But now one bond got broken, right? So now the third carbon has 3 bonds in it now because it has made a new bond with this. So there'll be a plus charge on position 3. So whatever the position 3 is, there'll be a plus charge on there. All right. This is where the chlorine would come. It was HCl, right? H plus, Cl minus. Tell me, what do you think about this reaction now? This exact question actually came in JE in the yesterday's paper. So how was the question? Wasn't it really tricky? Very difficult to get or something? All right, that's why, guys, we need these kind of classes where we are talking about these extra topics that we have not really familiar with. Is the introduction clear? Guys, write it down. Carbocation part. This part. Why is the carbocation that thing? See, it's just like this. Let me show you real quick. It's going to be a little bit difficult to show you from a bond point of view. So I'm just going to use my gestures here. So here what happens is, just focus on this molecule for the time. So here actually what happens is, there was a bond between carbon number 4 and 3. Now, considering the bond that you can see here, how many bonds are there for carbon? This carbon bond number 1, bond number 2, bond number 3, and there is an hydrogen. There are total 4 bonds, right? For this, how many bonds are there? Bond number 1, bond number 2, so definitely 2 hydrogens are present. Now, what did I do over here, guys? Now have a look. What did I do? For the bond shift, I broke this bond first. With carbon number 4 and carbon number 3, I broke this bond, right? Then I added the bond over here with carbon number 2, right? So now the carbon number 3 has 1, 2, and 3 bonds, because the other bond which was connected to carbon number 4, it is now broken. So there will be a positive charge on carbon number 3 then. Isn't it? Great. So are we clear till the end now? Till here, are we clear? Tell me now. All right. But the point is, oh, just a second. Where was I? Okay. Now the question is, this is the second major product, but not the major product. You have the hint right here in this molecule. From this molecule, something can happen. This is not the major product, guys. This is the second major product. What can be the major product? Think about it. Here's the second major product. What can be the major product? The hint is there in that molecule. So look into this molecule and try to figure it out. What would be the major product here? Everything? Very good, Laksha. That is 100% right. This is what they ask you in 25th January's shift. This question till here was there in yesterday's shift. In 25th January, what they did is they did the next step in here, which is now it's gonna undergo hydride shift again. Because so far it's a 2-degree carbocation. Now after this hydride shift, it would become a 3-degree carbocation. That's why, guys, I tell you to check the papers, the JEE papers will. Now it would become a 3-degree carbocation. See, every single things are connected over here. So now the chlorine would come into that. This is the final product. So what do you think? What is the level of difficulties for this question? 1 being the easiest and 10 being the hardest. Tell me, Gokul, Laksha. What do you think? What is the difficulty level of the question? Right now, you might be thinking, okay, no comment. Anything? See, if you see this question right now, as you have just learned it, you'd find like it's a lot of things are going on over here, isn't it? Don't you feel the same way? Like there is a lot of things that you have to keep in mind, the hydride shift, the bond shift, the methyl shift. But like I said, it's kind of a habit. Okay. We also, the first time when we looked into this questions were really very difficult for us. But over and over again, when we started looking into these kind of questions over and over again, that is when we got the idea how to solve them. So it's like it's all about practice. It's all about the culture you are in, right? If you just solve the questions which is around there in the NCERT only, yes, they are going to ask you that kind of questions. But that doesn't tell you that you won't be able to solve these questions. Practice in the higher level than whatever they are going to ask you. That is when you can crack the questions easily. All right. Now, this was the hydride and the methyl shift related questions and everything. One more thing that I can tell you right now is how to understand whether that we are bond migration or not. So first of all, you'll be able to see whenever you get the ring below 6-member, whenever you get the ring below 6-member, always remember it has a potential to make the rearrangement, the bond shift, because 6-member is the highest stable, the most stable molecule. I mean the rings, with respect to the rings. Even 7-member is less stable than 6-member. Okay, 7-member also has angle strain. 6-member is the most stable. 5-member is also close to stability, but 6-member is the most stable. So whenever you see there is a molecule with 3-member ring, 4-member ring, 5-member ring, always remember it can take a step to get into a 6-member ring. All right, let's solve one last question for today's session. Don't miss these classes. These are really super important for us. All right. Let's say I have a cyclobutane system, and over there I've added an NH2, and then we have a CH3. They're asking what would be the product if I give NaNO2 oblique HCl, and the second reagent that we are going to give is just add any kind of a basic. Okay, just add any kind of basic, any OH, any NH2, anything, any basic. So what do you think, guys? What will be the product? Close, Lakshya, but see what are you writing over here? How many carbons are you going to write? I'm writing base, all right, not nucleophiles. I'm writing bases. Yeah, take your time. Got anything? NaNO2 and HCl would make it diazonium salt, right? Diazonium means N2 plus Cl minus. Then you have CH3. Now what would happen is, guys, this N2 is going to leave the system because it would undergo SN1 mechanism. Because you can clearly see it's a 4-member ring. And I told you, whenever there is a ring lesser than 5 or 6 member, lesser than 6 member, it always has the potential for a ring expansion. And for a ring expansion, guys, you have to make sure that it is undergoing a SN1 mechanism. Otherwise, if there is no carbocation getting formed, it cannot undergo ring expansion, right? Then give it the numbers. So carbon number 1, carbon number 1, carbon number 2, carbon number 3, 4, 5, and 6. Now, how the ring expansion is going to happen? Any of the bonds. Like you can take carbon number 3,6 bond, or you can take carbon number 3,4 bond. Any of the bond. Ask it to expand. Okay. When you ask it to expand, what you have to do is, first it was a 4-member ring. Right now it would become a 5-member ring. So make a 5-member ring now. Right. And next, what are we going to do, guys? The carbons which are connected, carbon number 6 and 2, we are going to draw them. 6 and 2. Then add the rest of them. So 6 is connected to 5, 5 is connected to 4, 4 is connected to 3, 3 is connected to 2, 2 is connected to 1. This is how we draw it. Okay. Now, after this, as this bond has broken between 3 and 6, this is the bond which has been broken, right? As this has been broken, so there'll be a plus charge on this. Sorry. As this bond has been broken, and this is the bond which is connecting to 2, right? So what is the plus charge then? Tell me. This 6,3 bond has broken, and 6 is connecting to 2. What is the plus charge on carbon number 3? all right, because that is the bond which has been broken and not regenerated. So that's why carbon number 3 would be having a positive charge. All right. Now I'm giving a base. Base who takes hydrogen? Base are the one who takes hydrogen. Now see, which hydrogen is it gonna take? See, after taking a hydrogen, it's actually trying to make a double bond system in here. Okay. So it can take either this hydrogen and make a double bond, or it can take this hydrogen and make a double bond. Which hydrogen will it take? Let's say option number A or option number B. Which one would it go for? If it takes option A, then what is the alkene you are gonna get? This. If it takes hydrogen number B, what is the alkene you are gonna get? This. Which alkene is more stable now? Tell me, X or Y? Which one is more stable? X or Y? How do we actually figure out the alkene stability? Hyperconjugation. Hyperconjugation tells you about the alkene stability. How do you understand hyperconjugation? By alpha hydrogens. So if you have more alpha hydrogens, that means you have more hyperconjugation. More hyperconjugation means more stable. So see, if this is the alkene, how many alpha hydrogens do you see over here? See, 3 here, 2 here. So total 5 alpha hydrogens, 5 hyperconjugations. What about this alkene? How many alpha hydrogens do you see? 1, 2, 3. 3. Which one is more stable? Y. This is my final product for this question. Okay. The topic that I taught you the entire session today has a name which goes by Demyanov rearrangement. The thing that I taught you is known as Demyanov rearrangement. You can search about this and you can learn more and more rearrangement like this. In the next session, I'll be continuing with some of these kind of a rearrangement a little bit more. Then we'll be going into the name reactions, all the name reactions which is there in organic chemistry, and then we'll be completing the organic chemistry in that way. Then we'll be going to inorganic and physical chemistry later on. So that will be it for today then. Bye.
Thank you, sir.